building this fantastic system, this PanSTARRS system, which is going to be the best system ever in the world for identifying asteroids and comets.
And needless to say, a lot of animals and plants don't survive, and so there have been all these mass extinctions in the past from killer asteroids.
And the other thing people may not realize is there's no instructions that come with these devices. There's no stuff you just go out and buy. We actually designed all this stuff at the University of Hawaii and built and assembled and programmed it ourselves.
So one of the primary goals of PanSTARRS is to find asteroids and comets, and especially we're interested in asteroids and comets that someday might hit the Earth. Now, maybe some people may not know what asteroids and comets are. It's actually a pretty good question to ask. Asteroids are like large chunks of rock. They can come in any size, anything from the size of grains of dust up to something the size of Texas. Right? There's a huge range in the kinds of asteroids that there might be out there. Comets, on the other hand, are more like snowballs. Now, comets are not pure ice. Comets can be ice mixed in with dirt. And also, asteroids are not exactly pure rock either. So we're starting to see that asteroids and comets maybe really aren't so different. And you can think of an asteroid maybe as an icy dirt ball and a comet as a dirty ice ball. Okay? So think about these asteroids and comets. They're going around the sun. They're going around the sun in kind of orbits like our Earth does, right? They're not going around the Earth. They're going around the sun, just like all the planets do. Mercury, Venus, Earth, Mars, Jupiter, they all go around the sun. And most asteroids go around the sun in orbits between Mars and Jupiter. And there's millions of them there. There are tens of millions of them there. And that there's like 1 million of them out there that are larger than 1 mile in diameter. Okay. Now sometimes those asteroids that are in that belt out there, we call it the main belt of asteroids between Mars and Jupiter, sometimes they can hit one another. When they hit one another, they can catastrophically disrupt each other. And they can create a whole bunch of fragments, and the fragments will again range in size from dust to very large objects that may be tens of miles across. It turns out that when these asteroid collisions take place, sometimes the collision can be so violent that it can throw the asteroid into an orbit that eventually can bring it into contact with the Earth. And that's what we're really concerned about, because when I say contact with the Earth, what I mean is a giant impact. Okay? We do not want asteroids or comets to impact the Earth.
Some of these asteroids are actually pretty scary. They're called near-Earth asteroids, or potentially hazardous asteroids, or killer asteroids. And indeed, the Earth gets whacked every now and then by an asteroid. And it gets whacked very frequently by little asteroids. They're called meteorites, the shooting stars that actually hit the ground. But if you wait long enough, you will get hit by a bigger and a bigger and a bigger asteroid. And in fact, some of the impacts that we've had in the past are really quite scary. I mean, for example, Hudson Bay, you've noticed that kind of circular outline? That's probably a meteor crater. And when these really, really huge asteroids come down, like 10 miles across or 5 miles across or something like that, they create an explosion that's so big that it not only basically destroys things all over the planet, but it also really wrecks the ecology. And the planet itself takes a long time to recover before it's a healthy place for creatures and plants to live. And needless to say, a lot of animals and plants don't survive, and so there have been all these mass extinctions in the past from killer asteroids.
When we talk about the impacts, we always talk about terms like 65 million years ago, 100 million years ago, 10 million years ago. But the last major asteroid impact occurred less than 100 years ago. It occurred in 1908. And it occurred in a region of the world that is relatively unpopulated, and that's why not a lot of people know about it. It occurred in Tunguska, which is an area of northern Russia, which is essentially nobody lives there, a bunch of reindeer. But this impact occurred by a very small asteroid. It was something maybe only 50 yards across. And like I said earlier, the asteroids smaller than about 100 yards in diameter don't really make it to the surface of the Earth. And in fact, this asteroid that was about 50 yards in diameter did not make it to the surface of the Earth. The asteroid slammed into the atmosphere of the Earth at 20 miles per second, and the pressure, basically the shock wave that built up around the object as it was entering into our atmosphere was so strong that it blasted the thing apart in the atmosphere. And all that made it to the surface of the Earth was the blast wave. Now, even that blast wave was strong enough to knock down trees that were 1 foot in diameter 5 miles from the impact site, or from what would have been the impact site had the asteroid made it to the surface of the Earth. Right? So it's only been in the past 25 or 30 years that people really become aware of the danger that asteroids and comets pose to the Earth and to humanity. In fact, the odds of an asteroid impacting the Earth in the next 100 years is about 1 in 1,000. Right? So if you think about, if I told you that your house had a 1 in 1,000 chance of being destroyed by fire in the next year, you'd probably want to do something about it. You'd probably want to buy some kind of insurance or something like this. So I think it's the same kind of a thing, that if you think about the Earth having this danger of being hit by a very large asteroid in the next 100 years as being 1 in 1,000, that's in your lifetime, that's in my lifetime, and certainly within our children's lifetimes. We want to protect the planet. We want to put a little bit of an investment into this procedure. So about 10 years ago, the U.S. Congress finally began to realize that this is actually a danger and something that we could do something about. And more importantly, it's actually it's a natural hazard, but it's a natural hazard that we can actually really solve the problem. So what we need then is a system that can identify these asteroids and comets as they're going around the sun before they hit the Earth. Right? We want to find them before they hit the Earth because we would like to be able to do something about it.
Early on in the project, we had a committee of external scientists and professionals to give external oversight, and they looked at it and they made the suggestion that rather than try to go to a complete system right away, to build a prototype, because the system was pushing the forefront in so many different levels. Normally in science, you're pretty comfortable trying to expand the envelope in one particular direction, and with PanSTARRS it was recognized that we were trying to do a whole new level of detector development, and a whole new level of software and computing would be required to handle the absolutely enormous data stream. And so people were concerned that by pushing in those two different directions at once, developing this magnitude of the size of a camera and this extensive software system to reduce the data in real time, which is critical, that we would really have our hands full learning how to do that. So to start off with a single instrument and build our way up, build a prototype, learn how to do it, and move on from there.
So anyway, we're standing in front of, or I'm sitting in front of PanSTARRS. This is Haleakala. It's 10,000 feet. Mauna Kea is in the background at 14,000 feet. PanSTARRS is this dome right back here. It's actually not a very big telescope as telescopes goes. It's only about 6 feet across in terms of the mirror. And of course people have now built 10-meter telescopes, and they're talking about 30-meter telescopes and so forth. But what PanSTARRS does that's really different is it has a very wide field of view, so it can suck down a lot of sky at once. I mean, the large telescopes basically have a field of view that's like looking down a little soda straw, whereas PanSTARRS has a field of view which is 6 times as broad as the full moon. It's really quite a lot, and doesn't take too many of our pointings to cover the whole sky. And so that's what this whole project is about, is basically sucking down the whole sky and not doing it once, but doing it many times.
Well, one of the things that's particularly important to remember about the whole process of PanSTARRS is that it's a big data problem. We get a lot of data, and the number that comes to mind easiest is that we get every 30 to 40 seconds an image from the camera that's about 2.5 gigabytes, or basically a DVD worth. And over the course of a night, we can get several hundred, 500 or 600 or 700 of these images, and they all have to be processed and they all have to be stored. So to do the storage, we have a big cluster of computers that are going to be installed at the Maui High Power Computer Center in Kihei. We have a data link, a fiber optic cable that runs from our telescope from the Summit building down to this site in Kihei. And all the data gets transferred down to this big cluster of computers, and we basically have to have a very, very large data storage.
We've been working very, very hard on this for 4 years now, and we've, as I say, built this telescope, which isn't very big in terms of collecting area. On the other hand, its ability to make very sharp images over a very wide field of view is unprecedented. And we've also built the world's biggest camera to take advantage of this. Our camera comprises about 1.4 billion pixels. It's about 16 inches by 16 inches on the side. It's a lot of pixels. And to give you a scale of it, basically every time we read out this camera, we save an amount of data that's comparable to a movie, a DVD. So click, we take a picture, it's Spider-Man 1. Take another picture, it's Spider-Man 2. Take another picture, it's Spider-Man 3. We can read the camera out and take a picture every 6 seconds. And over the course of a night, we expect to take about 1,000 pictures every night. And then over the course of the year, it's going to be, 365 times that, or at least as many nights as are clear. And so that's a lot of data.
It's a little quick description of what the electronics is I think everybody's familiar with digital cameras, and what they may not know is what actually senses the light is a little device called a CCD in most cases. And it's made out of silicon, and it converts light to voltage. And everybody is also familiar with, as technology progresses on, you get more and more pixels. Those are the actual individual little sites that can sense light. And the more pixels you have, the more resolution or the better picture quality you get. So like in a few years, there's a difference from a very old camera to a newer camera. Then this is a video camera. You can see the little chip inside. This is the size, so it's actually really big by commercial standards, of one of our devices. And we have 64 in our focal plane. So it's a really big digital camera, and that presented a bunch of really interesting electronics and software challenges to us to build something to do that. And the other thing people may not realize is there's no instructions that come with these devices. There's no stuff you just go out and buy. We actually designed all this stuff at the University of Hawaii and built and assembled and programmed it ourselves. So we ended up with a box about this size, and you may ask, why is it so much bigger? The reason is a box this size can handle 8 devices, so 8 of these, and these are quite a bit bigger, and not only just size bigger, but have a lot more pixels than these. And so what we did was we made some electronics that actually has a computer for every 2 devices.
Bringing in people and trying to conceptualize all the different kinds of questions that we can ask all the way across the entire breadth of astronomy, we can put together a series of surveys that address these questions and catch the interest of scientists all the way across the realm of astronomy. And that's one of the real powers here is this ability to use the data over and over and over and over again. And that is the same set of data is used for doing asteroids, for studying the solar system, for studying the Milky Way, for studying galaxies, for studying exploding stars, black holes in galaxies, the structure dynamics of the universe. All of these things can be done with the same data set, with the same people looking at the same data, but looking at it through a different set of spectacles, through a different set of scientific expertise.
The consortium itself shows you the scientific interest in this project, because before it was a project that just the University of Hawaii through the Air Force was working on. Once the telescope now that it's getting close to being operational in a scientific sense, now there are more than 200 scientists who are involved in trying to pay for and use just the PS1 telescope results. And that's an international 200, not just Hawaii, not just the United States. This is truly an international effort. And I think that really gives you a feel for why, or the breadth of the impact of this project, is that this is going to impact virtually every stage of astronomy.
There have been sky surveys before, and every time something new is turned up. What PanSTARRS is doing differently is a couple of things. First of all, our acuity, the sharpness of our images is going to be way better than anything anybody's done before. And that means that we can see things which are much fainter, and also without that blurriness that you get in previous sky surveys, you can distinguish close together things much better. But the other thing that PanSTARRS is going to be doing, which is really kind of unique actually, is this revisiting the entire sky over and over and over again. So why are we going to do that? Well, basically because we're looking for things that are actually changing or moving.
The PS1 survey doesn't track an individual asteroid. What we do is we survey the whole sky, and then we come back and survey it again, and we look for differences. And by looking at those differences and all the differences in those things, we can identify what things have moved from one time to another. And so we don't track individual asteroids, we don't look for them. Instead, we're looking at everything at once. And then we go back and figure out what's moved.
Well, basically between 200 yards in diameter and about 3/4 of a mile in diameter, we know very few of these objects. We maybe, like I said, we know 10 or 15% of them. And PanSTARRS is essentially designed to find 90% of those objects that are larger than 300 yards in diameter. So PanSTARRS is going to make a huge contribution in the next 10 years to finding these leftover dangerous asteroids. Not necessarily the ones that are going to wipe out the planet. Those have already been found, or at least 80% of them have been found. But PanSTARRS will find 90% of the rest of the hazardous objects.
Well, who gets to use all this data? Is at the end of the day, all the data will be released to the entire world. Maybe you've seen Google Sky or Google Earth. Okay. Same idea. Ultimately, all the data will be out there so that everyone can pan around the sky and see what's out there. And you'll have this time-dependent movie of everything changing in the universe, all the things moving in the solar system, just the differential rotation of our galaxy, the three-dimensional map of the universe and how things are changing over the period of time. All of that will be available to everyone.
Now, it seems kind of natural to say, okay, so we're going to do this survey, we're going to find the asteroids, and then once we found the asteroids and we find one that might hit the Earth someday, the question is, what can we do about it? It's kind of the same question you can say about tornadoes and earthquakes and hurricanes. Yeah, we might be able to predict where they're going to move, what path they might take, what the probability is that they're going to hit a particular city or not. But then you got to decide, what are you going to do? Are you going to evacuate the city? Are you going to wait a little bit longer until the hurricane decides which way it's going to go or not? The great thing about the asteroids is that we have, like I said, the ability to predict when they would impact to within seconds, long in advance, many years in advance. So we could, at the very least, decide to say that, okay, well, we know this asteroid is going to impact in this particular location on the Earth, and then we can decide how much damage it would create based on how large the asteroid is, and we could then decide what area to evacuate around that possible asteroid impact. And that kind of path might be something we might want to do for a relatively small asteroid impact. If we knew that there was an asteroid that was, say, just 200 yards in diameter that was going to hit, that was going to wipe out maybe 50 square miles or something like this, or 500 square miles even, we could choose to evacuate all the people that are in that area. On the other hand, if there's an asteroid that's 3/4 of a mile or a mile in diameter that's going to hit us, then you really don't have the option of evacuation because it's going to wipe out 1/4 of the planet. Okay, and you can't evacuate 1/4 of the planet. So then you have to be a little bit more creative about it, and you have to think about deflecting that asteroid. You can't move the Earth. The Earth is extremely massive, very large. You can't move the Earth. So the only option then is to take that asteroid that is going to slam into us and to deflect it very slightly so that its path no longer takes it to where the Earth is going to be. So there's a lot of creative people out there who are working on some clever ideas on how to actually deflect these asteroids. And one of the more interesting ones, I think, because it's sort of benign and kind of simple and very environmentally friendly, let's call it, is this idea that was come up by a guy who is now an astronaut. His name's Ed Liu, and he actually studied here at the University of Hawaii's Institute for Astronomy. And he's come up with this idea, along with a few other guys, of something that he calls the gravitational tractor.
So let's say sometime in the next 3-4 years, we start seeing Rob and Dave's and Nick's name in the newspaper a lot because they have issued a warning that they have found an asteroid with, let's just say, 1 in 10,000 chance of hitting the Earth. So what do we do about it? What you want to do with an asteroid is not to blow it up. What you have essentially done then is to take in a rifle bullet headed at your head and you've turned it into a shotgun blast. Are the Are there big pieces? Where are there big pieces going? I don't know. And there's really not much of a way to tell if you were to try and blow it up. Well, the beauty of orbital mechanics, or the study of how things go around the sun or under the influence of gravity, is that it's something that we understand very, very, very well. And it turns out that even though let's take this example of this asteroid going around the sun, and it's going some, say, 100,000 miles per hour at average speed, even a very, very, very tiny nudge will change the orbit and therefore the time that it takes to go around the sun. It turns out a very, very, very tiny nudge is enough to change the time it takes to go around the sun. Who here has ever tried to move a big boat up against a dock? You're trying to pull it in on a rope, and you pull and you pull and you pull and you pull and you pull, and it's not seeming to do anything. And then then eventually it starts to creep in, and the lesson learned there is that you don't have to pull very, very hard. You just have to pull for a long time. One of the things that we realized is that if you take a small spacecraft and you put it near an asteroid, well, there's gravity pulling them together, okay? Which would pull both the spacecraft towards the asteroid and the asteroid towards the spacecraft. We call this spacecraft a gravity tractor. And it's a pretty simple idea, and we're all pretty certain it'll work. And if you work out the numbers, the surprising thing is that tiny force of gravity between the two, some fraction of a pound, a few ounces, when added up is enough to give the small nudge that you need to keep an asteroid from hitting the Earth. Now, of course, this whole thing depends upon our friends here with the PanSTARRS telescope being able to tell us exactly where that asteroid is and which way we should pull it. Thanks.
So the possibilities there are endless, and the possibilities for young people to come along and look at this, because it has to be the young people that will come along in this new age to pick up this thread, because it is a new age, and the older people can't look at the data in a new way anymore. And that's the wonderful thing about science. That's why it's always the young people that are making fantastic discoveries in science, is because they can look at it in a different way. And here we're going to have so much to look for, so many things to go to look through, so much new data, and this approach of just literally opening our eyes. I mean, that's what PanSTARRS literally is. It's just an opening of our eyes to the sky, just watching the sky, just observing. It's just out there every night watching the sky. That's how you learn. If you want to study people, you people watch. If you want to study the universe, you go out at night and you open your eyes and you watch. And that's what we're doing. We open our eyes, we're watching, we're recording it, we're taking down all that detail. And then the understanding is what comes from going back and going through all of that and trying to understand what is it exactly that we've seen. And that's where the new physics, the new appreciation, the new understanding of the universe around us, the formation of the early stages of the universe, the formation of our own galaxy, the formation of our solar system, the formation of the planet Earth. All of this is buried in the details, and by simply opening our eyes to the night sky, we have the opportunity to try and increase our understanding of who we are and where we are in the universe. And that's something that has to appeal to everybody.
We're sort of in an age that's kind of equivalent to the time of Magellan. When Magellan did his voyage in 1500s, it was the first time anybody, or at least any ship, had gone all the way around the planet and had traversed all of the different oceans. And in some sense, Magellan was the first one to find all the continents, to be able to see all the continents. And we're sort of approaching that era now, because galaxies like this are kind of like the current continent of the universe is filled with galaxies that look like that. And at the moment, we're still looking in the dark, and we don't know a large fraction of the galaxies that are out there. Within the next few decades, we will get to a point very soon where we will be able to detect every galaxy like that has ever formed in the universe, all of them. That means that essentially from then on, it's no longer finding big continents, it's finding the little islands, the small little pebbles, and refining the maps. And we will we are really entering an interesting age of astronomy where we're finding out essentially all that we are going to be detecting all of the things that we can potentially detect at a certain scale. So it's a very unusual way of thinking about the universe. There is this whole, we have the ability as humans to actually go and observe all of the galaxies in the universe, or all of the stars in our galaxy. And that's actually pretty amazing. That wasn't possible until now.